Oh, that's much better. Okay, so what we want to talk about here is how do we find the empirical formula. Right? So I'm guessing that that you guys have kind of maybe wondered at some point, like, why this guy, right? Why not this guy, right? Why does this one exist and this one doesn't? You guys not wondered that? No? Okay, cool. That's okay. That's totally fine. So that's totally fine. The Lewis structure, when you're doing the connectivity of the atoms, usually can explain why one of them will form and one of them won't, right? But in terms of how we know that this is the chemical formula, we haven't actually talked about that at this point. So that's what I want to talk about here. How do we find the empirical formula? So basically, one of the ways that we can find an empirical formula is by smashing molecules at really high velocities and then separating the pieces by mass. That's called a mass spectrometer. And so the information that you get basically is I put in X grams of some compound, right? And I got the mass percent of each element in the compound. So the mass percent of an element in a compound is equal to the mass, or the molar mass is what we're going to be using most of the time, of the element or the atom times however many there are sorry guys, it's getting ugly, divided by the molar mass of the compound. Okay, so that sounds really complicated, but it's not. So let's look at methane for our example. So we have carbon and 4 hydrogens. We want to find the mass percent of each element, right? So we first have to find the molar mass of methane, of carbon tetrahydride.
Would be the atomic weight.
Yes, exactly. So that's going to come from the periodic table, right? So we have carbon has 12.011 grams per mole, and hydrogen has 1.008 grams per mole, and there's 4 of them, right?
My calculator. Oh, it's 16.043.
Perfect. Right? So that's the molar mass of the compound, right? Now for the mass percent of carbon, right? we're going to take the molar mass of carbon. We don't need to multiply it by any number because there's only one of them. Does that make sense?
Mm-hmm.
Yeah. And then we divide it by 16.043 grams per mole. Ooh, it's a percentage, so we need to multiply by 100. My phone's having a really hard time focusing today, huh?
I got 74.868%.
Does that make sense, guys?
Yes.
Cool. So, so how would you guys go about solving for the mass percent of hydrogen in this compound?
The same way.
That's one way, right?
Yeah.
Or you could just subtract it from 100%.
Yeah, baby. So when you only have two things in a compound, right, you can just subtract the difference of this guy from 100, right? And that'll tell you the mass percent of this guy, right? Now, I think it's a good idea to do it both ways, right? Just to make sure that this is kind of one of those fail-safes to make sure that you're doing everything correctly. Because if you don't get the same thing when you do the subtraction and the full math version, then that would be an indication that you're doing something kind of wonky.
Okay.
So let's do it both ways. 76, was it?
74.868%.
Oh, I got it different.
$25 point.
Or 25.132.
Does that make sense, guys? So let's do it the other way just to double triple check. So we know that the molar mass of hydrogen is this, and we know there's 4 of them, divided by 16.043 times 100 gives us
I got the same number.
beautiful. Terrific. Hooray.
Yeah.
Questions about that one, guys?
And I do have a really silly, dumb question.
No, it's not dumb. What's up?
I woke up 5 minutes before this. So,
I wish that I could say the same. I've been up since 5:50.
What?
oh,
Yeah.
what? No.
Yeah, this is so the difference in having a toddler and not having a toddler. I remember the days when I slept in until 10, 11, noon, sometimes 2 o'clock in the afternoon. So, I used to bartend, so it was not unheard of.
I thrive when I sleep. Okay, but my question, so the 100 that we subtracted
Yes.
from
Mm-hmm.
is just because there's 1.008 grams per mole in that. Like, why'd you
No.
do 100?
So, anytime you have 2 quantities, right, and you're doing the percentage of each, the percentage of each have to add up to be 100.
Right.
Does that make sense?
Yeah.
So if we know that A is this, right, then we just rearrange to solve for B. That's not a stupid question. I'm sure somebody else was thinking that.
I was like, wait, what?
Where'd the 100 come from? Yeah, for sure.
Makes perfect sense. I will not forget that. And okay, cool.
Does that make sense, guys?
I have a question. So for molar mass, is it okay just like a molar mass of atom is just round and like for oxygen, just say 16 to getting easier?
Yeah, absolutely. So in terms of the molar mass, you don't want to round too much, but I'm not going to mark you off for being, just a skosh off, right? But there may be questions, especially because of the nature of how we're doing this class now online, where you may not have the opportunity to show work. And so if you round too much and there's a small number that makes that difference in the problem, I don't know. What I'm trying to get at is it's better not to round, right? And there may be problems where it does matter, but I'll try to minimize those types of problems, if that makes sense.
Yeah, thank you.
Yeah. So Zainab, you can go back to the last page on when we post the video. Is that all right? Or did you have a question about that? Okay. Because we're going to do more examples, so we're not done yet. Okay, so I hopefully think, and hopefully you guys agree with me, that mass percent is not too difficult, right? It's just using what you know about molar masses and figuring out the percentage of an atom in a molecule, right? Mm-hmm. So where things get a little trickier is when you start with the mass percents of elements and you have to find the empirical formula. Okay? So, this is where things, I wouldn't say they get trickier, but it's a little more challenging. Oops. So, what I want to do is look at one of the problems from the homework packet. So, the chapter 6 homework. Number 2. All right. So the problem says we have butadiene. I'm terrible at pronouncing the organic names, you guys. I apologize. A component of butter and body odor, has a cheesy smell. Super gross. Elemental analysis of the butadiene gave the mass percent composition as carbon being 55.80%, hydrogen being 7.03%, and oxygen being 37.17%, right? And so the first part of the problem is asking us to find the empirical formula. Right?
So my first thought would be to just take them out of percent right away.
And do what with them?
Look at them and admire them.
I love it. I love it.
Okay, or find the mass of each element.
Yes, exactly. So what we're going to do, first step is we're going to basically just pretend I know chemistry problems starting with pretend are really not the thing you're ready for. Pretend that
No.
these are masses, right? And then convert to moles. Okay? So I'm going to flip to the next page so that I have room to write my gigantic writing. But that's our first step. So whenever we're looking for an empirical formula and we're starting off with the mass percent of the elements in the formula, we want to just pretend like the percentages are masses, right? So we had, oh, now I need them back. We had 55.80 grams of carbon, right? We're pretending. We had 7.03 grams of hydrogen, and we had 37.13 grams of oxygen. Okay, so we want to convert to moles. Okay, so for carbon, what do we need to convert from grams to moles?
Molar mass.
The molar mass, exactly, right? Just straight from the periodic table. So we see the molar mass of carbon is 12.011. And what unit is going to go on the bottom?
Grams per carbon.
Grams of carbon, and 1 mole of carbon is going to go on top, right? Remember, the number from the periodic table always belongs to the grams, right? It's always some number of grams per 1 mole of whatever we're talking about. Does that make sense? So 1 always goes with this guy in the molar mass. So it's 12.011. So what do we get?
4.646.
Yeah.
Like that? Did I do it? Cool. And the units are moles of carbon. Okay?
I think it's 4.646.
4646.
4.646.
Okay, well let's just do that because I don't like more numbers.
No, 64, not 46. 4.64.
Oh yeah, she's right. It's
Okay.
4.64.
Thank you, thank you. I'm just gonna rewrite that.
I wrote it correctly instead of incorrectly. Sorry.
That's okay. We'll get there. Cool.
Dyslexia.
Okay. Everybody with me on that one?
Yeah.
Cool. So then next up, we want to convert hydrogen, right? So what's going to go on the bottom here?
And
1 gram.
1.008 grams of hydrogen for every 1 mole of hydrogen.
oh, 6.97. I want to just make that 7. Oh wait, we're not rounding.
Nope, we're not rounding here. We're not ready for rounding yet. And now last up, we can convert oxygen grams to moles. What number is going to go on the bottom here?
15.999. I got 2.32.
2.32?
Yeah.
So everybody comfortable with what we did so far? So first thing, pretend like they're grams. Second thing, convert to moles. And then we're going to divide each number by the smallest number of moles. Okay, so we have three numbers here. Which one is the smallest?
Oxygen.
Oxygen, exactly, right? So we're going to divide both of these guys and this guy by this, okay? So here we have 4.64 moles of carbon divided by 2.32 moles of oxygen. We have 6.97 moles of hydrogen divided by 2.32 moles of oxygen, and 2.32 moles of oxygen divided by 2.32 moles of oxygen. And we'll talk about why we're doing this once we've done it.
So the first one is 2, right? And
Mhm.
then second one is 3.00 or 3. And then the last one's 1, right?
Mm-hmm.
Is there ever an instance where you would get like a point and you have to round?
Yeah, but basically there are examples of that. You don't round. You have to multiply each one by a number until you get to a whole number.
An even number. That's disgusting.
Yeah. It's not that bad because I would never give you anything that was crazier than like 0.5, right? Which if you just multiply by 2, NBD,
Yeah.
right? But I would never give you any of the crazier ones. You may see some in the homework, but I don't even, there may be like 1 or 2, but I doubt it. So, okay, what the heck did we just do in this step? So what we did was we figured out the ratio of carbon to oxygen, right? We figured out the ratio of hydrogen to oxygen, and the ratio of oxygen to oxygen is obviously just going to be 1, right? So what this is telling us is that for every 1 oxygen, right, we have 3 hydrogens, right? And for every 1 oxygen, we have 2 carbons, right? That is the empirical formula, right? So all we need to do to put it into its chemical formula is use these numbers as our subscripts, right? Hydrogen will be 3 and oxygen will be 1. I think I've officially killed my second pen now.
And that's what is the
This-
name dianine, whatever that is.
This is the empirical formula.
Okay,
Cool.
of that.
Yes.
Got it. Okay, cool.
Right? So this is the answer for part A. Right? So does that make sense, guys? Any questions about how we got there? So just to reiterate here, we first went from percentages, percent by mass. We pretended like they were masses, right? and we converted them into moles. Once we have moles of everybody, now we're looking at the molar ratio of each atom relative to the smallest number of moles, right? Now the reason we use the smallest one to divide is because that gives us whole numbers here, right? If we were to divide by carbon instead of oxygen, right, we would get fractions here, and that's ugly. Nobody wants that, right? So we divide by the smallest number of moles to ensure that we get as many whole numbers as we can. Does that make sense, guys? Cool. Other questions about that part? Okay. Cool. So now we can move on to part B. So we know our empirical formula was C2H3O, right? And part B is asking us for the molecular formula. Specifically, it gives us another piece of information, which is, ouch, that the molar mass of butadiene is 86.09 grams per mole. Okay? So, we know what the empirical formula is, right? And we know what the molar mass for the molecular formula is. Okay? So, in this case, the first thing we want to do is figure out what the molar mass of the empirical formula is. Right? So, we have 2 times 12.01 grams per mole plus 3 times 1.08 grams per mole and 1 times 15.998 grams per mole. So what does that give us?
I got 43.045.
0.045?
Yeah.
Cool. You guys with her on that one? It looks good to me.
Yep.
So, if we know that the molecular formula is just the empirical formula times some number, right? Some integer value. Then what we need to figure out is what number did we multiply this guy by to get this guy?
2.
Yeah, so it's pretty easy to see here that it's 2, but let's just do the math formally so you guys can see how this works, right? So what we're doing is we're trying to solve for this number, right? So we're going to take the molecular formula mass and divide it by the empirical formula mass, right? So we'd have 86.09 divided by 43.045, and indeed we see that that gives us 2, right? So what this means is that our molecular formula is just the empirical formula multiplied by 2, right? So what coefficient is going to go next to carbon?
4,
Exactly. 4
6, 2.
and 2, right? So this is the molecular formula, right? Now, if we wanted to double triple check and make sure we didn't mess anything up here, right? We could find the molar mass for this guy, right? If it doesn't match the original molar mass, then we did something weird and wild, right? Does that make sense? Questions about that, guys?
This is a lot easier than the molar coaster. I'll tell you what.
Honestly, the molar coaster, once you guys get used to it, is not that bad, right? And I would say that right now we're in kind of the more challenging part because we're looking at atoms and molecules. And generally speaking, when we go forward in problem solving, we really don't care how many atoms or molecules there are, right? So when we start doing stoichiometry with reactions, we really only want to know about how many grams or moles there are of something, right? So avocado's number is really only useful when you're talking about atoms and molecules, and we really only do that so that you've seen it, right? So those parts of the calculation, that part of the molar coaster is kind of gonna not go away, right? We could still exactly. It's going to go down in terms of its relevance. Other questions about this, guys? So so we did the problem from the homework in chapter 6. I believe there are some problems in, actually, I'm not sure if there's any problems from the textbook about this, but there are a couple of example problems in the practice exam that give you the type of question that I would ask on an exam, right? So this question is a beast, right? This is a really, not really long, but this is the hardest version that you could see, right? Usually the kinds of questions that I'd be asking you on an exam would be, what's the mass percent of this guy in that compound, right? Or given these mass percents, what's the empirical formula? So only part of this question at a time. Given this empirical formula and the molar mass of the molecular formula, determine the molecular formula, that kind of thing, right? So you wouldn't see this whole problem in one on an exam.
Okay.
Cool?
Yeah.
Cool. Other questions about this stuff? Cool. So the main thing to remember when you're going through these problems, and I think I did, actually, I'm going to stop this. Hoppa.